All right, folks, what we're going to talk about in this video is we're going to talk about discontinuities in functions. And what we're going to do is we're going to identify that there are three different kinds of discontinuities that a function can have, or there's three different kinds of discontinuities that we are concerned with in this calculus class, okay? Now, before you watch this video, you really should review a video on vertical asymptotes, and review a video on holes in functions. Okay. Now I will briefly right now review how we end up with vertical asymptotes and holes in functions when we're given a rational function, and then I'm going to jump into discontinuities. Okay. Now, if you're given some rational function, and rational functions are fractional functions, okay? So let's say you have some function, f of x is equal to, let's say, x plus 2 over x minus 7, okay? So this is a rational function. Now, this function at x equals 7, so we take the denominator. If we take our denominator and set it equal to 0 and then solve, we get x equals 7. This function has the denominator equals 0 when x is equal to 7. Okay? Now, if I were to then plug 7 into the numerator, 7 plus 2 is 9, I would come up with 9 over 0. And you can't divide by 0 in math. Okay? So, and as far as I know, you can't divide by 0 in any other subject either. But whenever you have a non-zero number over 0, if you were to look at the graph of that function, at that x value, you would see a vertical asymptote. Okay? So a vertical asymptote is a graphical feature that you get whenever at an x value, at any x value, at an x value, let's call it c, okay, where you get not 0 over 0. So if it's not 0 over 0, then you would have a vertical asymptote. On the other hand, let's say that we had some other function, and let's say that it was x minus 7 over x minus 7 times x plus 4. All right? Now, in this particular case, if I were to plug a 7 in for x, I would have 7 minus 7 is 0, 7 plus 4 is 11, so I'd have 0 times 11, and then in the numerator, 7 minus 7 is 0. And when I plug 7 in, so g of 7 would be 0 over 0. 0 over 0, which is not a real answer, okay? 0 over 0 is also not an acceptable answer. Not only can we not divide by 0, but we certainly can't divide 0 by 0. So whenever you get 0 over 0, whenever you plug a number in, that indicates a hole in the function, okay? So that's just my brief review on vertical asymptotes and holes. If you don't really understand that, you want to go back and watch a full lesson on understanding vertical asymptotes and holes, okay? So now we're going to talk about discontinuities in functions. All right, what I've done here is I've drawn a rough sketch of a graph of a function, and let me show you, I was supposed to put something right here. Hang on, let me go ahead and put that in there. All right, let me show you what we have here. So we have this function, it increases, then it comes to a maximum here, a relative maximum, then it goes down. This is a hole in the function, and then it comes down here, and then it goes up, and then this dashed line is indicating a vertical asymptote in the function. And then it picks back up on the other side, it comes down the vertical asymptote. Now this function is not touching anywhere up there. Okay, whatever this x value is, let's say that this is x equals 2, okay, and then let's say back here this is x equals negative 3, and then this is an important point, let's say that this is x equals 7. That at x equals 2, the graph is completely undefined. There is no output value. These on the left side of 2 and on the right side of 2, this graph is going up to positive infinity. Okay, never touching, never meeting. Okay, but on the other side of 2, it comes down, then it curves a little bit, And then here, it just does, it stops at this value at x equals 7. So on the left side of 7, it approaches this height, but then it kind of jumps down here, and then it picks up at this value, and it goes over here and curves and goes straight down. Okay? So we've got this graph. And here's what I want to show you, is that there's three main kinds of discontinuities. The first kind of discontinuity we call an infinite discontinuity. The second kind of discontinuity we call a removable discontinuity. And the third kind of discontinuity we call a jump discontinuity. Okay? Now, what you have to be able to do is you have to be able to identify, you have to recognize what these discontinuities look like, either graphically, or you have to be able to know what they look like algebraically. So you have to be able to look at a function and know whether that function has an infinite discontinuity, a removable discontinuity, or a jump discontinuity. That's what I'm going to show you how to do in this video. Is I'm going to show you how to identify whether you are looking at whether there is a discontinuity, and if there is a discontinuity, what kind of discontinuity is it? Okay? Now, the first thing I want to tell you is this, and you may want to write this down, is if a function has, let's say has no discontinuity at an x value, the function, therefore, the function is said to be continuous at that x value. Continuous at that x value. All right? Now, what is a discontinuity? Maybe I haven't defined that yet. A discontinuity is simply a break in the function. A function is continuous if you can draw the graph of that function without picking up your pencil. If you can draw the whole thing without picking up your pencil, it's continuous, okay? So look here. See this graph right here? From here all the way over to here, there are no breaks in the function. So this function is continuous from here all the way over to here. But look what we have here. That is a break in the graph. It's a break. It's a hole. It's breaking up the graph. And therefore, at x equals -3, there is a discontinuity. Similarly, over here at x equals 2, we have a vertical asymptote. And a vertical asymptote is a break in a function. However, between -3 and 2, between x equals -3 and x equals 2, the function is unbroken. Therefore, the function is continuous from -3 all the way up until 2. After 2, you can see that the graph is smooth and continuous, but you can see at x equals 7 that there's a break in the function. And so that is also a discontinuity. So this graph has 1, 2, 3 discontinuities. And each one of these is a different kind of discontinuity. But between the breaks, between -3 and 2, and between 2 and 7, and after 7, the graph is continuous at all other points. And so what we say is that a function is continuous anywhere that it is not anywhere that it does not have a discontinuity. Okay? So the question is, what kind of discontinuities are these? Okay, well, this one right here, a hole, we call this a hole. Holes are also called removable discontinuities. Okay, so wherever there's a hole, you have a removable discontinuity. So that is this function right here has a removable at x equals -3. So we would say this function has a removable discontinuity at x equals -3. A vertical asymptote, we call that an infinite discontinuity. So whenever there is a vertical asymptote, that means that there is an infinite discontinuity. So this function has an infinite discontinuity at x equals 2. And then this is called a jump. Whenever the function sort of, I mean, literally, look at it. It jumps. It stops being here and it starts being here. It's almost like it jumped over a bunch of space and started back up. That's a jump discontinuity. So this function has a jump discontinuity at x equals 7. So graphically, this is how you recognize infinite removable and jump discontinuities. Okay? Now what we're going to do is I'm going to show you how to identify these three different discontinuities in an analytical function. Okay? Okay, so what I've done here is I've broken up into three sections: infinite, removable, and jump discontinuity. And what I'm going to do is I'm going to show you when you are most likely to see each one of these. Okay? Infinite discontinuities and removable discontinuities, you're most likely to see those with rational functions. So if you have a rational function, there's a very good chance that you're going to either have an infinite discontinuity or a removable discontinuity. Now, both of these discontinuities occur when the denominator is equal to 0. So we're going to say at the x value where the denominator is equal to 0. The same thing on this side. Removable discontinuities are going to occur at the x value where, or values where the denominator is equal to 0. So this is easy to notice, actually. All you have to do with any function is take the denominator and set it equal to 0. So let's say that I have f of x is equal to x plus 1 over x squared minus, let's see here, minus 3x minus 18. Okay? Now, in this particular case, we would need to factor the denominator. And if we factor this denominator, it becomes x minus 6 times x plus 3. Once it's factored, we can set the denominator, or each one of the factors, equal to 0. So x minus 6 equals 0, and x plus 3 equals 0. And here, the x minus 6 is equal to 0 when x is equal to 6, and x plus 3 is equal to 0 when x is equal to negative 3. So in this rational function right here, the denominator is equal to 0 at x equals 6 and x equals negative 3. And so this function has a discontinuity at both x equals 6 and x equals negative 3. So if you have a rational function, find out what x values make the denominator equal 0, and those are automatically discontinuities. The question is, are they jump discontinuities, excuse me, not jump, are they removable discontinuities or are they infinite discontinuities? Well, I'm going to give you that rule right now. It's an infinite discontinuity if the numerator does not equal 0 at those x values. So, if the same x values that make the denominator equal 0, when you plug them into the numerator, if they do not make the numerator equal 0, then it's an infinite discontinuity. On the other hand, if the numerator does equal 0 at those x values, the same x values that make the denominator equal 0, then it is a removable discontinuity. It's really that simple. So in this case, our x values are 6 and negative 3. So when I plug negative 3 in for x, I get 0 in the denominator. But when I plug negative 3 into the numerator, negative 3 plus 1, so f of negative 3 gives me negative 3 plus 1 is negative 2. I get negative 2 over 0. So is this a removable discontinuity or is this an infinite discontinuity? Well, the numerator is not 0. Not 0 means it's an infinite discontinuity. So this function, f of x, has an infinite discontinuity at x equals negative 3. Now let's plug in 6. What is f of 6? Well, when we plug 6 in the denominator, we get 6 minus 6 is 0. 0 times this is 0. So we get 0 in the denominator. But in the numerator, 6 plus 1, that's 7. We get 7 over 0. Again, the numerator is not 0. Therefore, this function has a second infinite discontinuity at 6. So let's sum this up. When you have a rational function, you can have either an infinite or a removable discontinuity. And the way you'll know whether it's an infinite or removable is if an x value makes the denominator equal 0, and it also makes the numerator equal 0, that's a removable discontinuity. But if there's an x value that makes the denominator equal 0, but the numerator does not equal 0, then that is an infinite discontinuity. There's also the situation where you could have a rational function where the denominator cannot equal 0. And in those cases, there is neither an infinite nor a removable discontinuity. Let's do a couple of examples. Okay, this one's an easy one. We have f of x is equal to 2 over x plus 5. Can the denominator equal 0? Yes, it can. If we take x plus 5, set it equal to 0, we can solve. Subtract 5 from both sides, and we get x equals negative 5. So we know that there's a discontinuity at x equals negative 5. Now, what about the numerator? Well, the numerator doesn't have a variable in it. So the numerator is always going to be 2. So when we plug negative 5 in, f of negative 5 is going to give us 2 over 0. Numerator, not 0. Denominator is 0. So that means this one has an infinite discontinuity at negative 5. Let's try another one. All right, look at this one. We got x minus 3 over x squared minus 9. Okay? So in order to find out whether the denominator can equal 0, we would want to factor the denominator if we can. We also could use other methods, like we could use a graphing calculator to find out if the denominator has any zeros. We can also use the quadratic formula if it's x to the second power. But this is a difference of squares. This is easy to factor. This denominator is the same thing as x minus 3 times x plus 3. And then in the numerator, we have x minus 3. So what's going to cause the denominator to equal 0? Well, there's two x values. X equals 3 and x equals negative 3. Either one of these will cause the denominator to equal 0. And therefore, this function has two discontinuities. One of them is at 3 and the other one is at negative 3. Now, to find out whether each one of these is either an infinite or a removable discontinuity, we will plug each one of these numbers, one at a time, each one of these numbers into the function. All right, well, if I put a 3 in, what's 3 minus 3? So let's do g of 3. Numerator, 3 minus 3, 0. So put a 0. 3 squared is 9, minus 9 is also 0. And so when we plug 3 in, we get 0 over 0. When we get 0 in the numerator and 0 in the denominator, that means it's a removable discontinuity. So here, at x equals 3 is a removable discontinuity. Now what about negative 3? Okay, so what is g of negative 3? When we plug negative 3 into the function, negative 3 minus 3 is negative 6. And then negative 3 squared is 9, and 9 minus 9 is 0. We get negative 6 over 0. By the way, this isn't actually equal to 0 over 0. This means that it's undefined. There's a hole there. Okay? Negative 6 over 0. The denominator is 0, but the numerator is not 0. Therefore, this indicates an infinite discontinuity at x equals negative 3. Let's just do a couple more examples, okay? Okay, so we've got this function h of x is x minus 4 over x squared plus 16. Now, you might get fooled by this. You might think that you can factor this, but this cannot be factored, at least not with real numbers, okay? This x squared plus 16, it does not have any zeros. It never equals 0. Anytime you have x squared plus, you will have no zeros. Even if you have x to the fourth plus, no zeros. Anytime you have an even power with a plus and a number over here that's not zero and not negative, okay, then you are not going to have any zeros. And because this denominator cannot equal 0, this function is continuous. It has no discontinuities at all. Let's look at another one. All right, let's look at this one. We've got x squared minus 10x plus 21 over x minus 7. Well, what's going to cause the denominator to equal 0? 7, right? X equals 7. All right, so there's only one discontinuity because there's only one value that can make the denominator equal 0. So what we're going to do is we're going to plug that 7 into the top and the bottom. So let's identify what is k of 7. Well, we know that if we plug 7 in the denominator, we get 7 minus 7, which is 0. Now let's plug 7 into the numerator. 7 squared is 49, minus 7 times 10 is 70, plus 21. Okay? Well, 49 minus 70, that's negative 21. Plus 21 equals 0. And so we have 0 over 0. And since we have a 0 in the numerator and the denominator, that means that this function has a removable discontinuity. So what we would say is that there is a removable at x equals 7. That's what we would say about this function. Other than that, you might say, well, what about at x equals 5 or x equals 0 or x equals negative 17? At all those other values, this function is continuous. Any place that the function does not have a discontinuity, the function is continuous. Okay? Now let's take a couple minutes and we'll talk about jump discontinuities. All right, so let's look at jump discontinuities. And in most cases, you're going to see a jump discontinuity, or you're more likely to see a jump discontinuity when you're dealing with piecewise functions. So I've given you a very simple piecewise function here as a quick example. So here's the idea. If you're going to have a jump discontinuity and you have a piecewise function, the jump discontinuity is going to occur at one of the transition values. So here, this piecewise function only has one transition value. This function transitions from x plus 3 to x minus 2 when x is equal to 4. So all the way up until 4, for all x values less than 4 and equal to 4, we would plug those values into this piece of the function. But once we get larger than 4, now we're going to plug those numbers into this piece of the function. And the question is this: we don't want to know what's happening at numbers a lot less than 4 or larger than 4. We want to know what's happening right at 4. And so here's what you do to identify whether there's a jump discontinuity. All you do is you just plug that number into both pieces. Plug that number into both pieces. If both pieces give you the same number, then it is continuous. If both of those pieces give you a different number, then there is a jump discontinuity. Okay? So let's do that here. We're going to plug 4 into this. So if we put a 4 here, what's 4 plus 3? Well, 4 plus 3 is 7, right? Now we're going to plug the 4 in here. What's 4 minus 2? Well, 4 minus 2 is 2. And because we got a 7 on one side and a 2 on the other side, that means that there is a jump discontinuity. And so basically, it's really simple. The procedure for identifying a jump discontinuity when you have a piecewise function is just plug your transition values into the pieces and see if they match. Okay? Let's try another example. All right, look at this piecewise function right here. And what I've done is I've made it a little more complicated. This piecewise function has 3 pieces. Now, if you're not comfortable with piecewise functions, you may want to go find another video and refresh yourself on piecewise functions, okay? But very simply, the basic idea is that any value of x that's less than 3 would be plugged into this piece. If you're trying to calculate a value starting at 3, at 3 up to 7. So if you want to plug a 3 in, you're going to plug it into this piece. If you want to plug a 7 in, you're going to plug it into this piece. Why? Because this piece has the or equals to on both of them. If you wanted to plug in 5, you're going to plug it into this piece. Any number between 3 and 7, any x value between 3 and 7 is going to be plugged into this piece. But if you want to plug in a number larger than 7, when x is larger than 7, you're going to plug that number into this piece. So a piecewise function is just telling you that depending on what your x value is, that function takes on different behavior. This one is a quadratic up until 3. It's a linear function between 3 and 7, and it's a radical function. It's a square root function at values of x larger than 7. Okay? So this means that this function, because there are two transition values, there's 3, and there's also 7. And because there are two transition values, this function could have up to 2 jump discontinuities. Okay? So we have to test both of them. We're going to have to test both of them. The way we test them is we plug the transition values into the functions. So for this one, for 3, we're going to plug 3 in here. Well, 3 squared is 9, and 9 minus 4 is 5. So now let's plug 3 into this piece. If we plug 3 in here, 3 plus 2 is also 5. And that means that this function, g of x, is continuous at x equals 3. Because look, we have the same number on both sides of 3. So it's continuous at 3. So now let's see if g of x is continuous at 7. We're going to plug 7 into the function. 7 plus 2 is 9. And put a 9 here. Now let's plug 7 into this. 7 plus 2 is also 9, but we have to take the square root of 9, and the square root of 9 is 3. And because these two numbers do not match up, there is a jump discontinuity at x equals 7. So here we would say jump at x equals 7. Okay? All right, so now we've covered infinite discontinuities, removable discontinuities, and jump discontinuities. And now what I want to do is I want to do 1 or 2 examples that combine all 3 of them into one problem. Okay, here's a piecewise function. And you'll notice in this one that 2 of the pieces are rational functions. And what that means is that now it is possible for us to have an infinite discontinuity or a removable discontinuity in the piecewise function. But not because it's a piecewise function, but because it has rational functions as a part of it. Okay? So the first thing we're going to do is we're going to look, and here's what you have to do. Look at each one of these rational functions and see what will make the denominator equal 0. Whatever will make the denominator equal 0, you then have to check to see if that number is a part of this domain piece right here. So we have x plus 3 here, right? Well, what's going to cause x plus 3 to equal 0? Well, that's if x is equal to negative 3. Is negative 3 less than 2? Yes. Therefore, negative 3 is on this domain, and so therefore negative 3 would be plugged into this, and therefore there is a discontinuity at x equals negative 3. But what kind? Well, we know that it'll make the denominator equal 0. Now we need to plug it into the numerator and find out whether negative 3 will make the numerator equal 0. Well, negative 3 squared is 9, right? That's 9. Negative 3 times 7 is negative 21, and then plus 12. 9 minus 21 is negative 12, plus 12 is 0, and therefore we know that x equals negative 3 will make the numerator equal 0, and it'll make the denominator equal 0. Therefore, this function has a removable discontinuity at x equals negative 3. Now let's move on. Let's go over to this one right here. This rational function, x minus 6 in the denominator, what would cause this denominator to equal 0? X equals 6, right? Because 6 minus 6 equals 0. Well, is 6 on this domain? This says whenever x is greater than 5. Is 6 greater than 5? Yes. Therefore, 6 is on the domain of this piece, and therefore 6 indicates a discontinuity on this function. But we have to plug the 6 into the numerator. 6 minus 35 is negative 29. And so we would have negative 29 over 0. This is not 0 over 0. Therefore, this 6 indicates an infinite discontinuity. So we have an infinite discontinuity at x equals 6. Okay? Now we need to check for jump discontinuities. This is a piecewise function. So we could potentially have a jump discontinuity at 2 and maybe at 5. And the way we're going to find out whether there's a jump discontinuity is we're going to plug these numbers into the pieces that they're next to. So we're going to plug 2 into these both, and then we're going to plug 5 into these both, and see if we come up with different numbers or the same number. So if we put 2 in here, 2 squared, that's 4, plus 7 times 2, that's 14, plus 12, okay, over 2 plus 3 is 5. Now 4 plus 14 is 18, and 18 plus 12 is 30. So we have 30 over 5, which equals 6. Okay, so we have 6. All right, now what if we plug 2 in down here? Well, 2 squared is 4, and 4 plus 5 is 9. So when we plug 2 down here, it's 9. When we plug 2 up here, it's 6. That's not the same number. And therefore, at x equals 2, there is a jump discontinuity at x equals 2. Last one to check now is 5. We're going to plug 5 into here and plug 5 into here. Well, 5 squared is 25. 25 plus 5, that's 30. Okay, now we're going to plug 5 in down here. 5 minus 35, that's negative 30, divided by 5 minus 6, that's negative 1. And negative 30 divided by negative 1 is 30. So when we plug in 5 down here, we get 30. We have the same number, and therefore that this function, f of x, is continuous at x equals 5. And so these are the discontinuities on this function f of x. Okay? We're going to do one more example, and then we're going to be done. Okay, here's another piecewise function. We've got 2 of the pieces are rational expressions, and let's start looking for our discontinuities. Well, the first thing I'm going to do is I want to see if there's a discontinuity in this rational piece. Then I want to see if there's a discontinuity in this rational piece. Then I want to see if the transition values, negative 3 and 1, might have jump discontinuities. Okay? So let's look at this first piece here. Well, I know that this denominator here, x minus 7, that is going to have a discontinuity whenever x is equal to 7. So I can plug 7 in and see if I get 0 on the top and the bottom. But before I do that, I want to see, is 7 on the domain for this piece? Well, this piece says that whenever x is less than or equal to negative 3. Is 7 less than or equal to negative 3? No. So I'm not even going to look. Even if, this piece isn't represented by the function when x is equal to 7. When x is equal to 7, I would plug it into this piece down here, and this piece is plenty continuous at x equals 7. So I'm not going to look for 7. I'm done with that piece. Now I'm going to move on to this piece. What x value will cause this denominator to equal 0? It's x plus 5. So whenever x is equal to negative 5, this denominator will equal 0. Well, let's see if negative 5 is on this domain. Is negative 5 greater than negative 3 and less than 1? No, it's not. It is not on this domain. Therefore, negative 5 isn't even going to be plugged into this piece. Negative 5 would be plugged into this piece, and negative 5 is not going to cause the denominator to equal 0 there. Therefore, there is no discontinuity on this piece. Now I just need to check for jump discontinuities. So I'm going to plug my transition values into the pieces that they're attached to. -3 goes with this one, and -3 also goes with this one. So I'm going to plug -3 in. -3 squared is 9. -3 times -9 is positive 27, so I'll put plus 27 plus 14. And that equals, let's see, 27, 37, 41, 50. That equals 50. Over, divided by, -3 minus 7 is -10. So I have 50 divided by -10 is -5. So when I plug -3 in here, I'll get -5. Now I'm going to plug -3 into this piece. -3 squared is 9 minus 19. That equals -10. Over -3 plus 5, that equals 2. And -10 divided by 2 is -5. So if I plug -3 in here, I get -5, and they're a match, -5 and -5. So there is no jump discontinuity from this piece to this piece. Okay? Lastly, we're going to test 1 in here and 1 in here. So if I plug a 1 in here, 1 squared is 1 minus 19, that equals -18. 1 plus 5 is equal to 6. -18 divided by 6 is equal to -3. So this, when I plug 1 in, I get -3. Now I'm going to plug 1 in here. 1 minus 4, that's also -3. We have another match, and therefore there is no jump discontinuity from here to here. And so because we haven't found any discontinuities on this function, we would say that this function is continuous. It is, let's see, f of x is continuous. Or we would say that f of x is a continuous function. Okay? So I hope this lesson on continuity and discontinuities has helped you. The next video that you're going to see me in is where I talk about the intermediate value theorem, and the intermediate value theorem is requires you to have an understanding of continuity. Okay, so good luck with this.